So you're me and you're in a geology lecture, and the lecturer is talking about making sure everything is in the right units, and about how you don't want to mix up your units, or you'll get all your maths wrong. But you're feeling like a rebel, so you decide that units are far too mainstream, and you want to think about dimensionless numbers, and rectangles, because rectangles are kind of cool. Units, not to be confused with UNIT, the Unified Nations Intelligence Task Force, are something that quantitative scientists bang on about. 25 what, they say when you produce a mathematical answer in class. Centimetres, foot-pounds, acres per weekend. Maybe I should back up. When we wish to express the value of something, its height, its weight, its volume, we must state what the numbers represent. This is done using dimensions, although it has nothing to do with TARDISes. These dimensions or units can be simple, like millimetres, or something more abstract, such as Pascal seconds, which is the SI, International Scientific, unit of viscosity. Simple units are determined by saying, okay, here's the unit length, let's call it an inch, so how many inches can we fit along this line? We could even make up a unit and ask how many pencils are along a table, and if we know how long a table is, say 2 meters, we can convert the meters into pencils and give the length in pencils. Or we could lay out pencils end to end and count them up. Don't forget that you're measuring the table in meters, but the pencil in centimetres. You've got to be careful, otherwise you'll get totally the wrong answer. Having an intuition for scale is very important if you're a scientist. More complex units are calculated by taking the equation for the piece of density you want to calculate, say density, and look at each independent unit in the equation, seeing what cancels out and what you're left with. So what are dimensionless numbers? Say I have two lengths, one 10 centimeters long and the other 5 centimeters long. When we divide one by the other we get 2, not 2 centimeters because the units cancel. We have found a ratio between these two numbers. If we then take a 100 centimeter long length and a 50 centimeter long length and divide one by the other, we still get 2. The ratios of these two sets of lengths are the same. This means that we can compare numbers and processes using these ratios. If these numbers were the size of a rectangle, we can say that these rectangles are scale models of each other. When scientists do experiments, they want to know if they are modeling things in a manner that's true to life. Since geologists can't build a full-scale volcano or create the extreme environments of the core and the mantle, they must rely on analogues, or models, that mimic processes on a smaller scale. This is where dimensionless numbers come in. Because they are just ratios, you can fiddle with the parameters until your dimensionless numbers for your models matches that of real life, for things like lava flows. Often science is about taking a complex problem and breaking it down into simple bits to work out what actually is controlling the processes. It takes a creative mind and some flair with physics to create useful dimensionless numbers, but when it happens, they can tell us whether liquids can shatter, if solids can flow, or if your model of Mount Fiji is to scale.